Welcome to Louis CS46K Programming Language, Structure and Interpretation of Computer Programs, Lecture 10, Tokenization. We will start Chapter 8, Lexical Analysis. And first part, we will work on the tokenization. So the objective is to understand what is tokenization, and then also understand how to use a regular expression, and also how to accomplish the ad hoc tokenization using regular algorithm. So let's look at it. Okay, number one, let's look at what is tokenization. Tokenization is a common task a data scientist come across when working with text data. It consists of splitting the entire text into smaller units. We call it tokens. In other words, we can call this the tokens as words. Okay, so every language we have words, and in programming languages, sometimes we call it tokens. Okay, so most natural language projects, most natural language processing projects have tokenization as its first step, because you have any processing, you read in data, you need to tokenize them before you can do processing. So that's the first step you need to do. It's called tokenization. So here in this chapter, we focus on talking about what is tokenization and how can we write some ad hoc tokenizer, okay, and also maybe teaching you the regular expression, extended Baker-Snor form for preparation of tokenization and lexical analysis. So text processing, lexical analysis, standard steps. Recognize language class such as English, okay, and recognize data document structure. So you need to know about the language, the document structure, and then broken into tokens of a type of markups, okay, type of markups. So for example, hello, how are you? You can break them into this way, and usually space and punctuation mark delineated, okay, and spatial issue with Asian language. Asian language usually is very difficult to break because Asian language is more complicated, okay, especially Chinese is very difficult to break them. The grammar is more difficult or some way, okay, and lemmatization, stemming, and morphologically analysis. Okay, here you have a few analysis you can do. What is left are terms stored in inverted index. Okay, so here text processing, there are several different steps. Okay, and text processing lexical analysis. Lexical analysis is the process of converting a sequence of characters into tokens. A program or function which performs lexical analysis is called lexical analyzer or lexer or scanner. These are the name for these lexical analyzers. So sometimes I use lexer, sometimes I call it scanner, sometimes I call it lexical analyzer. Actually, they are the same thing. They are what you have a input or input file. You go into a lexer and you create stream of tokens. Okay, and the tokens usually have the token value, token type, okay, and token position. Sometimes they have some, you can create a different tuples, okay, create a tuple of several data. So here, let's look at this one. It's not cool that ping pong is not included in Rio 2016. Okay, ping pong is a sport, but it was not included. Actually, it was, okay, but here I don't know. It's actually a sentence, okay, and it's not cool to do that. Okay, so we tokenize into words. It's called tokenization. Okay. And this tokenization is to split the text into minimum, meaningful, units. Okay, that's the goal that we have. Okay, so this is called tokenization. And these are easy that you actually can separate them by using the space to separate them. Okay. And if you have a period, usually you can convert period to space. So that you should be able to convert some English sentence into tokens. Okay, this is actually tokens. So chunks can be words, phrase, characters, etc. Okay, so that's number one. But here there's some issue. Okay, here there are some issues. So this is pure text split. You can get tokens, but there are some issues such as space, parentheses 1+2. Okay, so something like this. There's no space to separate them. How can you do that? You basically can actually when you see some parentheses, you can add space before and after it. Okay, and then you have one. And you will see some plus sign, you also add and put spaces. Okay, so in this way, you will have a parenthesis 1 plus 2. You don't have parentheses. You don't have spaces. And then next one, you do have a space, right parenthesis like this. Okay, so in this way, you automatically replace your original symbol with some space before and after it. You can still create the so-called tokenization into the right format. Okay, into the right format, so that we would study it later. Okay, so what tokenization did you use for real problem? Okay, for real problem, always ask this. Okay, a fundamental question for all text processing, natural language processing, text mining, machine learning, and AI, information retrieval and research. Okay, these all rely on the text processing. Okay, so basic index pipelining, you have some document to be indexed, and you pass through it to tokenizer. So you tokenize the so-called words, okay, with string. Then you actually pass through linguistic module. So friend, Roman, and countryman. This one, you actually make a little bit of adjustment from plural to singular, okay? And you can make some adjustment and then invert the index, okay? So these are something you can do for tokenization. From sentence to tokens, you can first break down to logical units, okay? Break down to word units, and then find linguistic module to replace plural to singular, okay? Something like that. Okay, so source call, you pass through some grammatical unit for parser, okay, and you can also pass through some lexical analyzer to generate token strings, okay, and these two can be one pass or talking together, and after that you produce abstract syntax tree, okay, and then you evaluate the whole tree, you get interpretation result, okay. So source program, you pass through lexical analyzer, you create tokens, and token can be passed to parser, okay. And parser can predict next token that you can use. So sometimes the parser and the tokenizer, they will have interaction, okay. But usually also have the symbol table that will help you. So these are the traditional compilers' ways of doing lexical analysis. Okay, so lots of tokenizer out there. Okay, so you have different type of things that you can help you to do tokenization. Number one, use split. Second, use regular expression. So today in this lecture, we use split and also a AHA tokenizer, and we will introduce regular expression, but the use of regular expression for tokenization will be saved for the next lecture, okay? And toolkits such as natural language toolkit, Spacey, Keras, and Jensen's, these different tools, we will not introduce them in this course, okay? So, okay, tokenization example, friends, Romans, and countrymen. You create tokens or words, okay? And these words are candidates for index entry, but because they may have plural or singular, you should you should try to actually classify them using the linguistic module to the right singular words. Okay, so issue for tokenization, you have Finland's capital. So Finland, they have possessive case. Okay, so you should handle the plural and the possessive case. Okay, Hewlett Packard, you can break down into 2 words or 1 token. Okay, so dash and quote mark sometimes it's create trouble. Okay, state of the art, you can keep it as a word or actually break them down. Okay, so these are some issues when you may face in the tokenization process. Okay, so simple one, let's look at tokenization by split. Okay, tokenization by split is easy. You read in the whole file in the batch process, easy for coding. Disadvantage for file get bigger, they will have memory limits and also have some issue. Okay, and it also has the issue with possessive term, plural nouns, and the grammatical issues. Okay, these are something you need to take care of. Okay, so here we can open the file for reading, and that is a file handler, and you read it in for the whole file that become a string, and the string strip is a string function will take out the extra spaces before and after the string. Okay, and after that we do split, and we will print tokens. Okay, we'll print tokens. So here there are some program we will get this. Okay, but a word with a quote mark you group together as a token. Okay, same thing here. We do not deal with it if you just use pure split for it. Okay, so there are some issue regarding this one pass reading by batch operation type tokenization. Okay, and you can do line by line tokenization. This one actually is using a smaller buffer, so more efficient, no memory limits. Okay, and the disadvantage is like it still has a problem with possessive term, plural, and other grammatical issues. Okay, but you can read line and then process it and then put a token into the tokens. Okay, and then you actually can read more lines. So this one is a prime reading structure. Read, evaluate, and then add it to the line, and then actually re-evaluate. Okay, read again. Okay, read again. So same thing, you got this. Okay, extension, you got this. So that is called the Reevaluate Print and Loop mode. Okay, and you can look at the toolkit. Okay, you can look at the toolkit, and you can the REPL mode can usually utilize the so-called tokenization a lot. Okay, before we go into the lexical analysis, okay, using scanner and regular expression, we will look into example using the file processing. Okay, so before we go into that, let's look at one example. Now let's look at one example. Okay, here that's actually let me open some sample file from the demonstration site. Okay, let me actually get the file. So basically, I'm going to look into the lecture, the call for each lecture. So let's go to lecture 10. So this lecture 10, I do have some calculator language. So let's actually look at the calculator language, such as this calculator language A program. Okay, this A program. This A program, let's actually copy it. Okay, copy it. Let's copy the whole file. Okay, so copy the whole file. I'm sorry, actually, let me copy the whole file. Okay, copy the whole file. So A the calculator, and then let me actually open a new file. Okay, open file. So I'm going to go to my demo site. Okay, demo site. So go to demo, go to demo 10. Okay, right here. Let's create a new program. Okay, a new program. So this new program that actually create text. Okay, is called a.kal. Okay, calculate a language. Okay, so let me open it. Okay, so that one actually let me save it. Okay, and that's good. Let me save. Okay, and then I'm going to go to lecture 2 for B calculator language. Okay, this one I'm going to copy. Okay, and then I'm going to put in the same directory as well. Okay, so I'm going to go to the demo site, demo 10. Okay, right here I'm going to create. Here I should create O file and create b.cal. Okay. Okay, let me create a new file. Actually, it's called b.cal file. Okay, this file, let me actually save it. Okay. Okay, so let me actually save them. Okay, save them. So then, okay, and these two files, let me look at it. Okay. So these two files, because they are not text file. Okay, they are not text file. So let me change it. Okay. So right here, I'm going to use view and then change the file extension. Okay, so this one, I will, this one, okay, I'm sorry. This one, I'll rename it. Okay, rename it delete.txt. Okay, keep it like this. Okay, same thing, this one, I'm going to remove.txt. Okay. Okay, finish. Okay, so right here, I'm going to delete this directory. Okay, so now I have two KL files. Okay, so here I'm going to actually open my directory. Right now, I'm going to open my directory to this demo site, lecture 10. Okay, so right here, I'm using this one. Okay, and here I have two calculator language. One is A file, one is B file. Okay, so now I'm going to do tokenization for the first one and the second one. Okay, and this actually, we will consider this thing is a token. Okay, this thing is the token, this one is a token, this one is a token, this one is a token. Okay, so we'll consider those are token. And anything start from here to here, this one we call it a comment. Okay, so comment we will kind of don't care about it. Okay, and this thing to the end of the line, we also call it comments. Okay, also call it comments. And here we have this one B. Okay, B. Okay, that is. So let's look at this one. Okay, let's actually create a program called token1.py. Okay, token1.py. So we do have a file, and the file will be actually created using open. Okay, and let's open a.cal. Okay, and get it or read it. Okay, so we open that file, and this time let's actually create a string. Okay, so actually let's do string f string. So f string equals f that, okay, read the whole thing and then trim the before and end. Okay, here we use a string. Okay, and file at the very end we need to close. So at this moment f string is a string. Okay, it actually is a string. Then next one we are going to create token for it. Okay, create token for it. So here we have a.cal, we are going to create token for it. Okay, we're going to create token for it. So here, actually, what we would do is like, okay, we are going to create token for every single one. Before we create token, what we would do actually is this, we need to process it. This we need to process, this we need to process this. Okay, so basically, we need to find all of these things. Okay, we need to find all of these things because sometimes you may have assignment like this. Okay, so you need to be careful that when you get the assignment signed, you need to request them. So here we will need to find the so-called index. Okay, we need to find the so-called index and process the different index. So this one we do work on it before. So let's do this one. Okay, let's do this one. So let's do the POS, okay, equals the FSTR, the index of This index of actually would be getting the so-called column equals. Okay, column equals. So we are going to find the index for this one, going through the whole string for it. Okay, going through the whole string for it. And let's look at the index. Okay. So Python index function. So Python index function, if you don't find it, you will. This one is for list. Okay. So here I'm going to find the string. Okay. String index function. Okay. Python string index function, you will find the location of the welcome. You will get it. Okay. It's actually the same as this one. Find will return -1 with the value not found. Okay. And index will actually return will create an exception. So you rather use a find. Okay, so find is a better function. So you would like to use a find. Okay, you would like to use find. That would be better. Okay, that would be the position of the word. Okay, and you can actually let's actually look at it. You can use a string find the location. Okay. And that's the find function. You can find function. Okay, it will give you the location. Okay, -1 if it's not 5. Okay, and you can look at the starting location that you try to find it. Okay, so let's do this one here. Okay, let's do this one here. So basically, let's do this one. So here we do have this one. Okay, so while okay, actually POS. Okay. Actually is greater equal 0. Okay, we do the following set. Okay, we do the following set. We keep doing it, and every time we will find a location, and we are going to print out the location. Okay, print out the location. So right here, I'm going to use POS +1. Okay, and I'm going to print out the POS right here. So we have one homework before. Okay. We have one homework before to find all the location of certain pattern, okay, of certain pattern. So that's wrong. Okay. So this one we will get 3 location, okay. 3 location is over here, okay. It's a different location for it, okay. So this different term that we actually will find it, okay. So this is correct, okay. This is correct, but now we want to repress them, okay. We want to repress them. So find, and then we would try to repress them. Okay. So here, let's do this one. Okay. So let's look at another function called repress. Okay. So string repress. Okay. String repress, it will. Okay. Python string repress, it will replace the banana with apple. Okay. And you will old value with the new value. Okay, there's a count value. Okay, count value specifies how many occurrences the old value is. Default is all occurrence. So this one is a way you actually find all the location. Okay, so at this moment, I actually copy this one to token 2. Okay, so let's copy to token 2. So this token 2, let's actually do this. Okay, let's do this one. Let's actually do. Let's do this one. Okay. So right here we may have function actually called define. Okay. Replace. Okay. Tokens. Okay. Replace tokens. So given a string. Okay. And we'd like to replace it by the tokens. So here for okay. T. Okay. T is a token. Token in token list. Okay. To the following, we actually do. I'm sorry. We actually do replacement. Okay, we do replacement. So we do fstr replace. Okay, replace your token with space plus token plus space. Okay, so that's actually replace in that way. Okay, that's replace in that way. So we will replace every single one of them using the function like this, okay? So this portion is actually cut them, okay, and put it in Mongo everything. These are the standard token and function we will use, okay? Okay, so the token list and the replacement tokens, okay, so we actually put in this, okay, and that actually do have this one, let's actually do replace, okay, tokens of the FSTR, okay, and we replace them. Then let's do this. Let's actually do print, okay. Before, okay, before and FSTR, okay, and after that we will actually copy and then actually after, okay, after replacement, let's actually print it one more time, okay. Okay, let's actually try this one. Okay, so this one actually, oh, I'm sorry, this one should be S, okay, should be S. We should change the S, okay, so here we get a new S, okay, so we actually do return, we should return S, okay. So our, let me see here, our FSTR should be replaced by it, okay, it actually is immutable, so we need to get a new S. Let's see, oh, okay. Run it, okay, let's see. A, we do replace, okay, we do replace. So here, this one, we replace, you create a new string, so let's actually assign it to my new string, okay? Sorry for that. Okay, so this one we do separate them in this way, okay? We do separate them in this way. So here we actually, division, we may not want to do it, so that actually take out the division, okay? Take out the division, that actually save it, because division for the comments, okay? So we do get this, okay? Time, we also don't want to do it, okay? So these are something that you can process, okay? Or you can actually take out the comments before you do replacement, okay? Before you do the replacement. So you can, those are something you can do. Okay, so here we do get this one out, okay? Okay, so that are tokens that we actually finish, okay? So these are something that we finish, okay? Let's try another one. This one is actually copied to token 3. So let's paste here, okay? This time let me use b.cow. Okay, save. And here let's actually run it. Okay, so b.cow also being separated by spaces, okay? So now that's, we got that, okay? So that's actually don't care about this before and after string now, okay? So we will do the following thing now. We are going to do tokenization. So we will do, I'm sorry, line, okay. Now we equals, let's see. Okay, I'm sorry. Here we have a whole string, we have a whole string. So we will do tokens, okay, it will be equals FSTR, okay, that split, okay, the split, using the split, and you will assign it to tokens, okay. So after that, we do print my tokens, okay. So this one is for my b.cow, and save it and run. And so right here, it actually broken into the tokens, okay, broken into tokens, okay. So this is same thing that actually copy to the token 2 as well, okay. So if you have something like a special thing you need to take care of, okay, such as a comment, you should take them out. And then before you split them with the tokens, okay, before you split them with tokens. Okay, so this one is my split result for the tokens, okay. But comment, you should take them out before you actually, you should take them out before you feed it into the tokenization, because these are not useful token units. Okay, so this is a short example of how to generate a token list. Okay, using the split method. Section 3, lexical analysis. In the previous section, we do look at a simple scanner using the split method, but it has limitation. Basically, the way we do it is just relying on the separator using space. So some of the symbol you may not have space, so you need to replace it by extra space to be able to tokenize them. But this still has some limitation, as we show in the previous example, that some of the patterns, such as comments, will not be taken. So it is not, the split method is not enough. So here, let's look into the detail for the lexical analysis. Overview scanner. We'll talk about the scanner in a formal way. And then we'll talk about from regular expression to non-deterministic finite state machine, the non-deterministic finite automata. And then from NDFA, okay, non-deterministic finite automata, to generate the DFA, and then minimization of DFA, and then present the scanner styles. So these are the official topic for scanner. So first, scanner, we already know that you read in some text from a file, and then scanner try to break them down into tokens. And because of the limitation of the split, some of the grammar-related issue for scanner may not be able to be implemented. So we need to have more advanced techniques to handle that. So you can use the yet and next to generate it, and you use a regular grammar and content-free grammar to generate the scanner or lexer, and also the parser, and also the symbol table. So this one is the optimal goal. But today we will be focused more on the systematical way to design a scanner. So this one is a calculator language that we use in the previous example. So basically, you have a sign that is actually a column with equal, and then plus, minus, times, division, left parenthesis, right parenthesis, and these are the so-called IDs, or so-called tokens, or operators. And then you also have the comments. The comments is defined over here. Okay, and you have the ID, and ID is written down in such a format, and we will explain it using the regular expression. So here, this one is something we need to take care of, a number. So here, we add one more issue into the tokenization. So originally, we are dealing with, say, 3 plus 5, okay, plus A112, okay, plus 25A4, okay. Originally, we just deal with the tokenization like this. Just tokenize the words as the tokenization we use using the split. Now, we will look into the validation of the tokenization. So first step is the tokenize. To tokenize them into tokens. Second step is the validation of tokens. So this one is not parenthesis. This one is a number. This one is a plus sign. This one A112 have to be a ID or variable. And this one 25A4 apparently is illegal. So we will add the concept of validation of token into here using the regular expression. And then some of the grammatical structure for Lexa that depends on the parser we also will cover, but not right now. So here the tokenization will involve the basic tokenization by a delimiter or the so-called separator. And second, validation and grammatical structure. So here we continue to look into the number 2 and number 3. Okay, so that is a calculator language. And recall scanner is responsible for tokenize the source. And we move in the comment. So comment will be identified and being removed. Okay, you can also call it the pre-processing. And often dealing with the pragma, this is also pre-processing. So these two portions are the so-called pre-processing. And tokenization, including the pre-processing in C language or C++ language, and saving text of identifier, number, and string. So this one is the validation of tokens. And you save them into the so-called symbol table. And the symbol table is in the previous slides. In the previous slides, it's in here. You will create token and put that into the symbol table. So that's the so-called saving the text of identifier, numbers, and string, and saving source locations such as file, line number, column number for error messages. So these are the responsibility of the scanner. So suppose we are building an ad hoc handwritten scanner for Pascal. We read the characters one at a time with a look ahead. So we may see a bracket, parenthesis, brackets, and less than, greater than, comma, colon, semicolon, equals, plus, minus, etc. Okay, these we call it tokens. We call it individual tokens, and some of them are operators, some of them are the block level delimiter. So if it is a period, okay, it is a period, we may need to look forward to the next one to understand what it's actually used for. Okay, so it can be a domain specifier, and it can have other that actually is a field selector. Okay, range delimiter. So it actually can represent different things. Okay, it can be dot, it can be domain specifier. Okay, it can also be a dot. So we have to look into its neighbor to determine the meaning of that token. So if it is less, and it can be part of the less than equal or individual less than. So we need to use a look ahead to decide whether it is a token, part of the token in the less than equal, or it's an individual token called less than. If it is later, we keep reading later and digit and maybe underscore until we can never. So basically, when we see a later, it can be A115 or A2B4. These are a symbol. But if we have 2A, and apparently that actually is wrong. So here we need to see the look ahead and determine a token. Okay. So now, if it is a digit, we keep reading until we have a non-digit. Okay, a non-digit can be a period. Okay, can be a period. If it is not a period, we announce it as an integer. Okay, and it can be also so you have 25, and it's not digit, a space. It actually is an integer, but you may have 25.24. Then that is a real number. Okay, so here you still need to rely on a look ahead to determine the status of your data. Okay, and if the character after the period is not a digit, we announce it an integer, and we use the dot and the river head. Okay, so here you need to be careful about dealing with the dot. Okay, so here is a deterministic finite automata. So we do not look into the systematic way of generating the non-deterministic finite automata. We haven't looked into the regular expression. So right here, that's actually directly jump into the final result, the final finite automata. Okay, you have identifier, integer constant, real constant, comment, and symbol. These are the so-called tokens. And we can design a scanner to be built in ad hoc format. So we directly use threading function to qualify the tokens. That's called ad hoc scanner. And you can use table-driven deterministic finite automata to be a scanner. And you can also combine half of the ad hoc, half of the table to become a semi-mechanical DFA. So basically, there are several ways you can write the scanner. And ad hoc generally yield the faster, most compact code by doing a lot of special purpose things. No good automatic generated scanner may come very close. So performance-wise, ad hoc scanner is better than table-driven, okay, or automatic generated DFA. But actually, it may development time may take longer, okay, because table-driven DFA, you can use compiler to generate it. So after the scanner returns the token to the parser, when invoked again, it repeats the algorithm from the beginning using the next available character of the input, okay, to determine. So that's called look ahead. As a rule, we accept the longest possible token in each invocation of the scanner. The full bar is always a full bar, and the never be F or full B. Okay, more to the point, in a language such as C language, 3.14159 is a real number and never 3. Okay, and dot and 14159. Okay, so these are depending on the grammar tool rules. White space is generally ignored. Okay. So here we actually look at the so-called ad hoc scanner. Okay, production compiler often use ad hoc scanner. That's the truth. Okay, because scanner is not that difficult to write. So usually it will be using ad hoc scanner, and you use a table-driven scanner just because that you can develop a scanner in a shorter time to prototype some compiler. Okay, so finite automata can be generated automatically from a set of regular expression. So in later half of this chapter, we'll talk about regular expression and making it easy to regenerate a scanner when token definition change. So that is easier when you have a change, and then after you have stable version, you may go back to the ad hoc scanner. So here, PQ 2.5 is a so-called ad hoc scanners pseudocode. So basically, you look into the so-called character, and then determine whether they are the token right away. If not the token right away, you can look at this comma, column, and then wait for the equal sign. If there's not equal sign, then there's an error. Okay, so here this one is a ad hoc scanner, okay, and pure token, and then tokens that rely on look ahead later, okay, and token with period, okay, that we actually is used for the real numbers. So here is the brief algorithm in pseudocode for the ad hoc scanner. So this one we will put into a state diagram like this. So state diagram is easier to understand. Right-hand side, we have the so-called grammar rule written in some kind of the regular expression, regular grammar, okay, regular grammar. And we can develop it into the so-called finite automata, okay? And these two things, grammar and automata, and the so-called pseudocode. They are the same. They are three of the same thing. So basically, from your regular expression or regular grammar, you can generate your finite state machine or automata, and this one can be coded using ad hoc algorithms. Okay, and that's the previous page, and then your input token will be given to here, input file, and you generate tokens after this. Okay. So that's the basic idea of this finite automata. So now let's look into a ad hoc scanner, okay, written by me. This one is section 4. So let's really look into the coding portion. So basically here we have a ad hoc scanner. You can find it in the lecture simple code, okay, lecture 10 simple code. We call it lexscan.py. So here you have the token type as a dictionary. So it's a token type and then token symbol, okay, token symbol and token type. So this one, we actually have that. You have it, okay. And then we have system variables such as file name. You read in the file as the input. And then you have the input string as str, and you have the state, the current state. This state variable will be following the number that we have in this finite automata. And then we have tokens, okay, that's a resulting tokens, and token has token type, and then they are tokens, temporary token buffer, okay, something that you would be used to create token, okay, you have token type as well. So now your main program, you read in the input file, okay, and then if the file not exist, then we say input file not found. Otherwise, we read in the whole file and then clean up the end of file or the white space later, okay, before it and after it, and we put it into a string. Initial state we set up to the state 1, and number of tokens we set to empty. Token type we don't have token type, and current token we set it to empty string. So this one actually starting the finite state machine from state 1, okay, from state 1. So from there, we actually start to look into the main scanner loop. For each symbol from the raw input string, we evaluate the current state and the character to determine the next state and tokenization. This one is following this state machine. So here, for example, you see a parenthesis that will be left parenthesis token, right parenthesis token, plus, minus, and times. And if you see a colon, the next one must be equal. If it's not equal, then you have grammatical error. And if it's equal, then that's a signed token. And then if you see a slash, okay, you see a slash, and it doesn't follow by slash or star, that means it's a division. That's a division. So we finish that. We will return to state 1. Okay. If actually it is a slash and after a slash, then we go into the state 3. So that's, we keep reading it until we see a new line mark. Then now we'll go back to state 1. Okay, that is comment. If we see a star, then we go into state 4. So it's the slash star. Okay, we wait until there is a star and followed by the slash, then we go back to here. So this is state 5 is that you have star, but in the middle you can have multiple star or non-star. It actually being bypassed no matter what. Okay, so basically we enter into the state 4 because of the slash star. This one is the beginning of the state, and then you have state 5 because you actually read a star, and you would get out of command line only when you see this. In the middle, you may have multiple stars and it doesn't count. It just continue to be in the state 4, okay? And in the middle, actually, if you see a non-star and then followed by non-star, then you go back to state 4 because it's not a closing star. It's not a closing star for comment. Okay, so this one we finish slash portion and single token portion, assignment portion. Then this one we see the digit and number. Okay, so you can have a number like with only one digit. So say 5. You go into here, you can finish, or you can continue with multiple digit. You can continue with multiple digit, and you can finish. Or you may have this with multiple digit, and then you follow by period and then several digit. Okay, that actually is a real number. Okay, and you can also have a point followed by digits, say 5555, and that actually is also a real number. So here deal with the integer and the real number. And then you may have a later and followed by the latest. But if you have the number followed by later, then that actually create error message. Okay, that's not what we want. Okay, so this portion is the rule. Okay, so here we generate the first portion not using the slash for division and the comment portion. So this portion we read in a slash. Okay, we will look ahead. Okay, so basically the next one is a slash or star. Okay, we're going to the state 2. Okay, otherwise it's not it. Okay, then we will determine it actually is a division and we'll get out. Okay, we'll get out. Okay, but if the slash actually is already the end of the file, if it's end of the file, then you do not have the 5 divided by 3. You do not have the 3. It is in the end of the file. So we will report error in that case. Okay, the second portion is a single tokens. So single token, you just check your state 1 with a single token, okay, and you will wrap up the token status right away. Okay, so generate token right away. Okay, next one you have star. Okay, generate the token right away. And if you have the column, you will be followed by equals, and then you will generate the assignment. Okay, otherwise you will create error if it's not followed by the assign. And then the next one is this one actually is the comment portion. So comment portion, you actually would check it. Okay, check it. If you are in the state 1, okay, and you get these different states, you continue to stay in the state 1. Okay, and then if you have the slash, okay, you have a state 2 and you see another slash, then you go to state 3, and state 3 going into here. Okay, going to here. Or you actually are in state 2 and you see a star. That means you enter into the state star portion. Okay, you enter into that. Okay, and if you are stage 3, okay, you see \n. That means you have slash and something, and then \n return. You go back to state 1. So we skip those comments already. Okay, if you are stage 3, then we actually do not generate token. Okay, so continue. And if we are state 4 and see a star, then you enter into state 5. Okay, if you are state 4 and you see a slash, I'm sorry, you are in state 4 and you continue, you're not going to generate everything. And if you are state 4 and then state 5 and then you see a slash, then you terminate it. And if you are state 5 and you see a state, you continue to state 5. Okay. Okay, and if it's not something else, you go back to the state 4. That is the embedded. Okay, that actually is the invalidation of your slash. So here you have slash star to go from here to here. Okay, and you may see a star, and if it is not following by slash, you go back to state 4. Means that this star is useless. You need to wait until another star to terminate the comments. Okay, next one we have the assignment digit and number and later ID. Okay, so here we do look into a dot, a single dot, then we will go into stage 13 and check the digit. This one is this branch. Okay, this one actually is this branch right here. Okay, going to here. Okay. Okay, going to there. And then we have state 1, and then if it's directly being the digit, then we start to look into here. We accumulate the token now. We accumulate token because we have to continue to check more token. Okay. And if it's state 14, we check if actually it terminates. Okay. If not, you actually try to see if it's actually terminated. Okay. If not, we continue to look at data, and that this portion are evaluating this portion. Okay, the state 14 and state 15 is actually going to here. Okay, that portion just going to here. Okay, and then state 16 is checking if they are the ID. Okay, they are ID. So then we actually can process this input A dot calculator language, okay, into such tokens. Okay, so 2 assign, and then 1, and then the common bin bypass, and then B assign 2, and then so here this top portion are tokens, lower portion are token types, will be generated by my next scan. Okay, and then here we have beta calculator. Okay, same thing, you will create the right format for us. Section 5, tokenization by regular expression. So far, we already know that a finite state machine for the tokenization is possible, and we can use that to qualify the input tokens and then check the grammar. So in this section, we are going to go a step further, trying to look into the issue of generating a tokenizer from the grammar. So let's look at this chart. You can design the language tokenization based on the grammar, and the grammar will be used to generate a finite state machine. So this finite state machine, you can use ad hoc method to generate the tokenizer, or you can use a table-driven way to design a tokenizer using automatic generator. So we already demonstrate how the ad hoc generator can be done, and also using the split method. And now we are looking into what is the grammar, and that can be used to generate state machine. And that can be used to take the input language and translate into tokens, and tokens used to generate the parser, and parser generate the target code. Okay, so here let's look at the syntax of Arabic numerals. So for example, we have digit. So each single digit will be 0 to 9. So we can describe it as this. This is a grammar rule. Non-zero digit should be 1 to 9. So natural number will be from 1, 2, 3, up to infinity, right? So it is what? It has a leading non-zero digit, and then with a digit that can be this, okay, repeating 0 or more times. So star, we call it clean start. Clean start will be repeating 0 or more times. So this one, we call it the grammar, and this is regular grammar. So let's actually look at this one more time. So basically you have digit, okay, so digit, you have digit, and digit can be defined as 0 to 9. If we are using the so-called regular expression, okay, if we are using regular expression, this is 0 to 9, okay, this digit. And non-zero digit, non-zero digit will be 1 to 9, okay. So let's use this one as D, this one as ND, okay. So your natural number will be 1 non-zero digit plus 0 or more digit, Okay, so this one we call it the regular grammar. Okay, and regular grammar can be written in regular expression format. Okay, so here we can also write it down as this. Okay, we can actually write it down as syntax diagram. So we have now 0 digit with actually 0 or more digit. Okay, like this. That is the so-called syntax diagram. Okay, so in this section, in this chapter, we are going to cover the following few things. Number one, regular grammar. Okay, number two, regular expression. Okay, number three, we will cover the syntax diagram. Number four is the extended Baker's norm form. This four things actually sometimes can be interchangeable and can be the same thing. So we are going to use this to do tokenization for tokens that have special grammatical position. So in the first few sections, we talk about tokenization by simply dealing with the tokens by separation and adding extra space for separation. That's the first thing. And now we are talking about tokenization that has the grammatical union. And we can draw the syntax diagram that is, okay? This portion is repeating 0 or more time. This one is actually now 0 digit, okay? So you write down the little digit and a digit repeat for 0 or more time. Okay, so this one is a representation for natural number, and we call this regular grammar. So a regular language over a alphabet sigma is one that contains either a single string of length 0 or 1, or string which can be obtained by using the operation of the following: union, concatenation, and clean start. Okay, union means that you actually put them together. So you have one language like this and another language like this, you actually combine them together. That is union. Concatenation means that you combine the symbol from one language with the other. And then clean start, you can repeat in them. So it actually is intercept, complement, and difference operators that can be used to build a formal language. Okay, so context-free grammar. Context-free grammar and context-free language is more than the regular language. So it actually will have the step. And right here, for tokenization, we basically do not need this one. Okay, we do not need this one. So, but here you can have a V is digit, non-zero digit. Okay, these V are the vertex. So that these are some node or some state. Okay, terminal and non-terminal. Okay, and sigma is the alphabet. Okay, and then R is the rules, or R is the rule. V is a vertex. Okay, S is a starting state. Okay. So expression, grammar, and language. These are 3 in 1. Okay. Grammar is something that you define your language. Okay. Grammar is something that you define your language. Okay. And then expression is something you describe by the grammar. Okay. So grammar is a set of rules, and language is all the composition of simple sequence that generated by the grammar. So grammar is English grammar, language is English language. Okay, expression is some way that you written down as a pattern for in that language. Okay, so regular expression can be used to describe the deterministic binary automata. Okay, and regular grammar can also be used to describe deterministic binary automata. Okay, and these two can generate the automata to accept the regular languages. Okay, to accept the regular. So grammar and expression can actually generate a regular language. So let's look at this one more time. So So the language actually is here. It will be qualified by your DFA, okay, deterministic finite automata, and deterministic finite automata actually can be generated from your grammar. Okay, so that's the relationship of these three things: language expression and the so-called language expression and the so-called grammar. Okay, 3 in 1. And this whole set can be used for the so-called YEC and LEX. Okay, this one is automatic generation. We'll cover this in the next lecture. Okay, but basically, you can write down your regular expression or regular grammar in LEX format. Okay, and generate a YYLEX. This YYLEX is a function for lexical analysis or Lexer, okay, in your language over here. So here, actually, this one is grammar. Here is DFA. Here you have language. So it's the same, or it is the implementation in C language for the machine we describe over here, okay, for the machine and grammar we describe over there. So why are we starting this? Okay, formally define a language using formal grammar. That's number one. We would like to define a language using the formal grammar. Second, we are utilizing the tool to generate the Lexer, okay, and also maybe parser in the future. Okay, so you can use the automatic generator for Lex and EX or regular expression thing. Okay, and you can design a compiler or interpreter based on the description of the language from grammar to generate the machine. Okay, now let's look at the scanning number 1, finite automata. So finite automata is the thing that we use in the previous section. Okay, we basically describe the calculator language in finite automata. Okay, so now we are looking into the finite automata one more time. So finite automata, we have the R, G, and M. Okay, G is the grammar, M is the machine, R is the regular expression. So the rule, the grammar, the machine, these are 3 in 1. Okay, 3 in 1. That means that you have one thing you can generate to the other. So let's look at the grammar first. So grammar here, you have G as grammar. Your starting state will generate this, and A state non-terminal. So little a is terminal. It's a single alphabet symbol. Okay, A and B actually are non-terminal. That will have its own generation rule. So basically, this set of grammar has 3 rules: S rule, A rule, and B rule. 3 rules. Okay, these 3 rules, and these 3 rules basically define the language. Okay, and these 3 rules can be translated into regular expression of this. Okay, regular expression of this. So that is the rule. So here you see you actually have a starting state. So your starting state may have starting with A or starting with a B. Okay, so you should start with A or B. Okay, A or B. So you have A or B. So if you start with A, okay, A later, and then is an A state. A state can have BBA. So repeating BB and with A state, or with a single B state, B symbol. Okay, so this one is the A rule. Okay, if you actually have the B state will generate a B later and followed by another B later. So actually B is starting with B later. Okay, and A is BB and then followed by A. Okay, so this is the rule. So this set of grammar is actually satisfying this regular expression. Okay, you have starting A or B, okay, and then BB or B repeating 0 or more time. Okay, so A rule, you will generate a single B or multiple BB or multiple BB. Okay, or multiple BB. Okay, so here you have, so basically this thing is like, this thing just saying that the first letter would be A or B. After that, you can have B or BB or B or BB. Okay, this actually no limitation of coming out with B or BB. Okay, and this thing we can use handwriting to generate the so-called machine. that is. Okay, so state one, you take input, you can have A or B, okay, A or B. So you may see a A, okay, you may see a A, okay, and you see a A, go to the state two, okay. State two, because your second part is actually 0 or more, so you may finish over here. Otherwise, based on the A rule and B rule, you will go to state 3 and state 4, okay, based on the way it actually generates, okay. So let's see. Here we actually generate AB, okay, so there's A or B. A or B, if you got an A, you may go to A and followed by with a B state, okay. A will actually have a BB. BB means that you go to, say, 1B state and 2B state, you go back to Excel, okay. So BBA is this rule, okay, BBA is this rule. And you can have a single B. Single B, you actually go to the termination state, okay. Single B, so this blue one is the rule for the A rule, okay. Blue one's the rule for A rule. Then your state two, actually here you have a single B, okay. If you start with single B, you go to the state 3, okay. So it will actually have a single B come to here. So it will actually come with the B and go to A state, okay. So it's this rule, okay. And or it with a single B, okay, and it actually will go to B state, okay, and keep doing that, okay. It will come back with B and then go back to AB, come back to here. So this is this rule. The real one is this rule, okay. So anyway, these 3 things are actually equivalent, okay. They can be proven to be equivalent. And what we would like to say is that regular expression and regular grammar and finite state machine are 3 in 1. So basically, if you can describe your regular expression, you are able to generate your finite automata. Also the same thing, if you can describe everything into the regular grammar rule, you can also generate it to the so-called machine, okay, finite state machine. And this whole thing actually can be generalized and also using the tool Flex and Bison to generate the next, okay. And we would cover this in next lecture, okay. So that's a 3-in-1 theory. And then we talk about regular grammar. So regular grammar is a mathematical object G with 4 components. N is the non-empty, non-terminal symbols. So vertex, you can call about this a vertex. Sigma is the alphabet, okay, symbols. And then production rule P, okay, production rule P. And then SS is the terminal, okay, S is the terminal. So basically that's a grammar. So let's look into go back to the previous slides, okay, previous slides. So here you have a starting state, okay, and you have production rule P, okay. You have your non-terminal A and B that actually are vertex, okay, and your alphabet A and B, okay. So this is sigma alphabet, okay, and this one is your vertex, okay. This one is your starting symbol and production rule. 4 things we actually call, in combination, we call it the regular grammar, okay, regular grammar. And a regular expression is one of the following, okay. So regular grammar is described like that, okay. And then now we are looking into the regular expression, okay. Regular expression is an expression that actually that can be used to describe a regular grammar. So it can be a character, can be an empty string, can be 2 regular expression concatenated, okay. So basically, a regular expression can be a single character, okay, can be an empty string, can be 2 other regular expression concatenated, can be 2 regular expression and actually separated by bar. That's actually 2 options, okay, 2 options can have the clean start. Okay, let's look at these things. Let's look at these things. Regular expression is actually is built up with these 5 different rules. So number 1, a regular expression, say a later I'm sorry, a string. So a string can have a single letter, say we have an A letter, okay, as a single letter, and it can be empty, okay, empty string. So your string can have a letter or can be empty string, okay. And it can also be concatenation of strings. So you have string 1 plus string 2. So say right now you have A string and concatenate with B string, okay, that actually is also a string, and can have S1 string or S2 string, okay. So right here, this one is another 2 string. You have the OR, and the last one you have the clean star, okay. Last one you have a clean star, so that you can actually here actually you can write in this way. You can have a string concatenate with a string, okay, or string or string, and then you have a string and then actually repeating itself 0 or more times. So here we define this one as a string, okay. So now actually let's look into this more, okay. So a string can define as A, okay, or B, or C, or up to any letter like G, okay. This is a string, okay. So this one we call it syntax diagram. Syntax diagram, okay. So you have option A or option B, okay. So this one, we write this down as S can be generated by A or B, okay, with a bar, okay. And you have different letters, so it can come from A to G for different route, okay, for different route. And same thing, the concatenation rule. Concatenation rule, your string can be A concatenate with B. That means that you have A string, okay, followed by B string. Okay, that's a concatenation rule. That's steal from another string. And then you can also have a string, okay, and repeat it itself for many times. So actually it's something that if we draw the clean star, it's something like this. You can bypass and happen no time. So this one is no time. And then you can repeat it with a string over here. And so you can go over it 0 time or many times, okay, that actually is the string. And you can have a single symbol of empty string, okay. So these are the regular expression, basic rule for regular expression, okay. These are the basic rule for regular expression. And with the regular expression, you can also describe whatever can be described by the regular grammar, okay. And regular grammar also is defined by the so-called grammar rule that we talk about here, the regular language rules, okay. Okay, anyway, that actually is the regular expression. So we talk about regular grammar and regular expression. And then next one here is a Becker's normal form for the numbers. Okay, this is the Becker's normal form. And actually, this Becker's normal form is written down in syntax diagram. Okay, so right here, in this lecture, we talk about regular expression. Okay, we talk about the syntax diagram. We talk about the Becker's normal form. So this reason actually, if you write down in one way, the other two ways can also describe it. Okay, so this Becker's normal form really is written in syntax diagram. So the regular Becker's normal form will introduce it later, but it is not in this format, not in the syntax diagram format. Okay, so here we have a regular language for the calculator language. Okay, so we define the digit, the exponent, the decimal, okay, decimal, and the real number, and integer and numbers. So number can be integer or real number. And integer has a digit followed by a 0 digit. Okay, real number has the integer, exponent, or decimal, and then followed by exponent or empty string. Okay, so these are the rules to define a numbers constant in calculators. Okay, so here we do go into the description of the grammar rule. For expression, you can define as term plus or minus term. Okay, a term can actually be formed by factor followed by star sign or actually division. So this one really means that, okay, you have 3 plus 5 times 2 plus 4 divided by 2. So this whole thing, we call it the so-called term. Okay, this is the term. So this one is another term. Okay, and these 3 terms form a expression. Okay, form an expression. So right here, 3 by itself is a expression. Expression plus expression plus a term is still a expression. Plus another term is still expression. So that's what expression is. Okay, a term is actually having a number. Okay, a term is 5 times 3. It is a number followed by a time and then actually with another factor. And factor can be a number or parentheses of something. That is called a factor. Okay, so factor is the component that a term will multiply or divide with. Okay, that's called factor. And the number is a formation of single digit. Okay, here number actually means the integers. Okay, and the digit is defined by this. So basically, digit define number, number define factor. Factor is any factor that actually A times B times C. This single one that you connected by time or division is called a factor. Okay, and this ABC can be an expression as well with parentheses. Okay, so this defines you the different term for digit, number, factor, term, and expression. All are in syntax diagram. So here we have expression. We can further token into here if no precedence. Okay, so time plus and division and multiply, no preference, then they will be flattened. Okay, in this way. So expression, number, and digit. This one is flattened format. Okay. Scanner number 2, scanner design. If we got a regular expression, how can we convert it to non-deterministic finite automata? Okay. So basically, this we talk about a 3-in-1 already. Regular expression can denote regular language. Regular language expression can be compiled to finite state machine. Okay, and finite state machine can accept the regular language. So these are 3-in-1 relationship. We talked about it already. So finite automata is you getting some input, it generates some output with some state in there. That's called finite state machine, okay, or finite automata. So right here, if we have regular expression, we have A, okay, then you actually from one state to the other. Okay, if you have A, B means the A concatenated with B, then you go from A and the next state. Okay, A or B, you actually go split to 2 output state. Okay, A star, clean star, you actually go back to itself. Okay, so this one is from regular expression to finite automata, directly translation is like this. Okay, so if we have the production rule, A to a terminal. Okay, A to a terminal, so A will start. So from state 1 to state 2, and we finish it with the A state. Okay, and if our A state is actually generate A symbol and then go to B generator. Okay, it will A and then followed by B and then go to state that would be A state. And this one is actually A and then you have A or B. Okay, so you go A or B and then 0 or more state, you will generate this. So here give you the idea of automatic translation from production rule to finite state machine, or the regular expression to finite state machine. Okay, or regular. So this actually is a tool that we can automatically generate the regular expression or regular grammar to automata. Okay, and automata can be used to generate the finite the program for Lexer, okay, for lexical analysis. And we show you by doing the ad hoc generator already. Okay, so first thing is that generating the finite automata. So first step is converting the regular expression to a non-deterministic finite automata. So basically, you use the automatic rule to generate them. Okay, don't care about whether it's actually good or not. So you convert it to non-deterministic finite automata, and then you reduce it to a deterministic finite automata, and then you minimize them. So to generate them by machine, we can actually have 3 steps. Okay, so let's look at it step by step. First, non-deterministic finite automata. So deterministic finite automata is that if you have a state 1, you have A, you can only go to 1 state. You don't allow a state with multiple outgoing edge taking the same input. If you allow it, then it actually is non-deterministic, okay? Because you get the input, you don't know whether we go A state or B state. So we call it non-deterministic automata. So deterministic automata does not allow it this way, okay? So the automata that have desired property that in action are deterministic is actually final, okay? In a given state with a given input, okay? A state with a given input never have more than 1 possible outgoing transition. That's called DFA. So DFA means that you have a state A, you got an A later, you can only go to a certain state. It does not allow second outgoing edge taking the same input. Okay, so that's a definition for deterministic finite automata. On the other hand, the non-deterministic finite automata, they may be more than 1 transition out of a given state labeled by the given character. So 1 input may cause different state. So this one actually in the implementation, it is not allowed. So that's why we automatically translate your regular expression to NFA. Then we still need to convert it to DFA to make it possible for design of Lexer, okay? So the so-called epsilon transition is that taking no input, you can make transition. That's called epsilon transition. So NFA said to accept string or token if there exists a path from start to final state whose non-epsilon transition are labeled. Okay, so constructing a NFA with a given regular expression. A trivial regular expression consisting of a single character C is equivalent to 2-state NFA, okay, illustrated by 2.7. So here we have 2.7. So here these are the rules that actually you can generate your NFA, okay. So given the rule, say if we actually have base case, okay, you got a character and you go to the next state is something like this, okay. And if you have alternate, so actually you actually from 1 state taking to a possible state, you actually have a bar, okay. You have a bar and you actually generate it this way, okay. And concatenation is like this, okay. This one is A followed by B, and this one is a terminal, okay. And clean star will be drawn as this, okay. So basically, this one show you that your regular grammar or regular expression in here can be mapped to a non-deterministic final state machine automatically using these A, B, C, D rules, okay. And that is the translation that we talk about over here as well, okay. And anyway, it generates a non-deterministic final automata, but that is not useful. You cannot apply it. You cannot apply it directly to the Lexer design, okay. So here you have an NFA transition. So you can take a D and you go to the next state, okay, or you can different rule. So you have decimal production rule, digit star, and then dot digit and digit dot, okay, and then decimal star. This whole thing, after we actually convert it, it will go to such a design, okay. So here, a dot go to the next state. D actually go to the next state. Okay. So dot D, D dot, these two things are here. Okay. And dot D and D dot, this whole thing you combine, it will generate here this portion. This one's this. Okay. And then your D actually with star will be like this. Okay. This one is this. Okay. And also this one is also this. Okay. So these two things are here. So we put this one here and this sample part here, and we get the rule for this one. Okay. So anyway, the end product for the NFA for this rule will be like this. Okay, will be like this. Okay, that's actually quick and mechanical conversion of your regular grammar to the NFA. Now, next one, we need to convert your NFA to DFA. Okay, we need to convert your NFA to DFA. So let's assume that we have a machine or a finite automata that's a DFA. So if you take the same input and then generates the same output, if they exist a DFA that take the same input and always will generate the same output, that actually your NFA will generate. So this is like this. Your NFA taking some input, you generate some output. And if this one actually compare with another DFA that actually also generates using the same input, would generate the same output. If these two always equivalent, then we say these two automata are equivalent. Okay. So basically the conversion is to find a DFA that generates the same result as your NFA. Okay. So here we have the algorithm to convert a NFA to DFA. Number one, create state table from a given NFA. Number two, create a blank state under the possible input alphabet for the equivalent DFA. Number three, mark the start state of the DFA by Q0. Number four, find out the combination of state of each possible input alphabet. Number five, each time we generate a new DFA state under the input alphabet. Number six, a state which contains any of the final state of the NFA are the final state of the equivalent DFA. Okay, these are the algorithms. We'll come back to here later. Okay, you may not understand it, but let's look at examples. So right here, we have non-epsilon case. If the grammar there is no epsilon or the final state machine no epsilon, we have an NFA like this, right? We have an NFA like this. So let's look at it. We have A or B star and B and AB like this. Okay, this is the language that acceptable here. Okay, so we have a state one. So state one, if we take A or B, will repeat as state one. So here, right here, before you take in anything more, this portion is in state one. You can take A or B. Okay, so take A or B, you will repeat at the state one. But if you take B, sometimes you take B, you may go to the state two. Okay, sometimes you may go to the state two. Okay, and then state two is that actually take a B. Take a B, and after that, you may take a A or B. So take another A in state two, you take a B, A or B, you will go to your termination state. So this one is your state transition table for this state transition table for this NFA case. Okay, and this is NFA actually accepting this grammar rule. Okay, so this is very clear. So let's look at this one with this state transition. How can we generate the DFA that accept the same language? So number one, we need to combine the state. So first, let's assume that the DFA's NFA state one is the new DFA's state A. Okay, so that one actually would take A or B. Okay, A may remain in state one, B may go to state one or state two. So here we have state one. So this state one actually is the A state. State A or one or two, it will be state B. Okay, so we will generate a state B because there's a spatial state needed. So state two is actually taking state one and two. Okay, so that state one or two, you take A, you may If state 1 take A, you must stay at state 1. Okay. Actually, if you take B, you will stay at state 1 or go to state 2. So these are two possible states. Okay. And also you take the B. So here, let's actually look at it. Okay. So you 1, 2, you combine 1, 2, you may combine these two and put it over here. Okay, combine this, you will put it over here. Okay, apparently you generate another state C and state D now. Okay, these are two different states, different from your NFA state here. Okay, so that's as you continue. So we create a state C and state D. So state C, you combine your state 1 and 3. Will give you a single and combine the 1, 2 and here. Okay, so here actually let's see. This one you combine this one and this one, you get here. Okay, this one you combine this one and this one, you get here. Okay, and this one actually is state A. This one actually is state B. Okay, we know that. So that's actually continue. Continue if we actually combine the state 1, 2, 3. State 1, 2, 3 together, you generate 1, 3. 1, 3 is state C. Okay, 1, 2, 3, 1, 2, 3 is your state D. So basically here you create the possible state combination. So we generate a final table of this. Okay, for DFA transition, and we can draw out a DFA transition as a final state machine like this. And this one is good enough to generate your ad hoc Lexical generator. Okay, so now if there is an epsilon symbol in the NFA, it will be taken in different way. Okay, it will be taken in different way. So here we have epsilon star over here. Okay, so if we have state 1, okay, state 1. So that's assuming this state machine is what we are starting it, and we are going to convert this state machine to a DFA. So we start with state 1. State 1, you take an A, you will go to state 2. Take B, go to nowhere. C will go to state 4. And epsilon not going anywhere, you stay at state 1. So this one is described in this way. Okay, empty string, you may repeat itself. Okay, that's the default condition. That's actually default condition. Then state 2, it takes epsilon, you will go to state 1. Okay, and you can also stay at state 2. So this one is epsilon state. Okay, and if you take a B will go to state 3. Take A or take C, you go nowhere. Okay, and then state 3 is a termination state. You take epsilon, you stay on itself. You take a you go to state 2. Okay, otherwise there's no more outgoing state. Okay, and then state 4, you actually take epsilon, you stay the same state, or you go to state 3. Okay, and then you take C, you go to here. Then there is no more outgoing H. Okay, so we can see that the right side, the transition table, represent the NFA over here. So both with epsilon case and without epsilon case, you just draw down your state transition table. Okay, you draw down your state transition table basically for your final state machine. Okay, for your non-determinate final state machine. And then after that, we are going to combine state. Same thing, we create A, okay, this one, and we actually create a, okay. So here from the original table, we combine A and empty string, okay. A and empty string, combine them together. So this one with this, we generate this, okay. B with empty string, so we cannot say. C, we actually combine the C, so actually you get a single C. Okay, C, you go to state 4. Okay, you go to state 4, and your state 4 will take a C and then go to state 3. So this one is what you get over here. Okay, because empty string, you will further go in there. You take C and then followed by empty string, you will automatically go to state 3. Okay, so this one you need to look at it, the combination of the states. So then we have a new state called 2-1 and 4-3. Okay, so we create B state and C state defined by this. Okay, so now we combine the state 1 and these. We take the A string and B string with empty string, and we should guard this. Okay, so you combine this 2-1, you got state 2-1, okay, with A merging with these, you got 2-1, okay. And then you have a B string merging with the empty string, okay, empty string. So empty string of this, actually you will get to B string and you will actually go to state 3, okay. And then you have the C string combined with the empty string, you get to 4-3, okay. We get to 4-3. You get to the 4-3. Okay, this one actually you take a B and then followed by empty string. So take a B, okay, you go to state 3, you follow by empty string, so you get this, okay. That's the following. Here you take a C, okay, this one you take a C from state 1, you go to 4, you go to 3, so you get to here, okay. So if you are 2-1, you combine these 2, you get a 4 or nothing. 4 or nothing, you only go to 4 at KC. So this one you get this, okay. Following this one, actually you see there's a new state called 4-3 generated. Put it over here, okay, this one's new. So this one 4-3 means that you combine these 2, you have an A, you actually have a 2 and nothing. 2, you go to here, you go to basically, you will go to 2 and 3, okay, 2 and 3, actually you have an A followed by, so you're 2, you go to 2-1, okay. 2 with empty string, you go to 2-1, so it's 2-1. And if you have B had nothing, by, and then you are not going to go anywhere. And then we have the C, actually you go to the state 3 with the empty string, state 3 followed by empty string will be itself, okay, so actually only, so by here, we do see a C extra state, this one originally here, okay, so we have one more new state generated. So that one is a 3 states. 3 state here, you take A is actually state 2. State 2 empty string 2-1, so you put 2-1 here. You have B actually going nowhere. C going nowhere. So here actually you finish the state transition table like this, okay? And you put the A, B, C, D to different state, you get a table like this. And that's the deterministic final automata that you will attend using this transition table, okay? So here we demonstrate how you generate from the so-called grammar rule to non-deterministic final state machine, okay? And then with epsilon or without epsilon, and then without epsilon, we are in this case, and you will generate a table like this, and the final automata like this. And then with epsilon, you start like this, and you will generate some final state machine like this. So basically, with epsilon or without epsilon, you will all generate deterministic final state machine. So you end up converting your DFA to this one. Okay, so this one is the grammar rule, the deterministic final automata that you obtain for this grammar rule. From here, you will be able to generate a deterministic final state machine like this. But this one has redundancy, so we will simplify this final state machine. So here we already finished the so-called 3-step. First step is generate the regular expression to NFA, and then NFA to DFA. Now we're going into the step 3, minimizing the so-called DFA. So minimizing the DFA is from here, okay? And then we go into scanner number 4. DFA minimization, section 9. So starting from regular expression, we have constructed the equivalent DFA, okay, and then we try to actually generate it, okay. So here, let's see, we have the final machine like this one, okay. So we try to combine the so-called the non-terminal and terminals, okay, final state and non-final state into two states, and we will see something like this, okay, ABC 3 state and D, E, F, G. So ABC are A state, B state, C state. These are actually non-final state, and D, E, F, G are final state. Double circle final state. Okay, so first step, we actually separate them into this step 1. But we do have ambiguity. So because we have D or dot, both have ambiguity. So we have the ambiguity. So this ABC must be split. Okay, ABC must be split. Otherwise, it won't work. Okay, we actually is non-deterministic. So the first thing is that we actually split out D with dot. Okay, and repeat. Okay, so here dot you actually can separate them. So there is a D, okay, and dot with D and dot without D, we will actually separate them in these two different states. So here your A with D you compute here. Okay, and dot actually you have two states with dot D and dot actually separate them. Okay, and you generate something like this, and then this one. Basically, you come from this one, okay, you separate them. So here you what? You still have the ambiguity of that, whether you go to here or here. So you have a D, you go to here, dot, you go to here, and after that, you followed by D, you go to D, F, G, and here you have D, dot, you go this way. Okay, and D, you repeat in B state. So here, by this one, you have no ambiguity. So if you look at B, you have D and dot. Okay. If you look at A, you have A and dot. If you have C, you only have a D. So no ambiguity. But right here, your AB still have ambiguity. So you further split down your AB to A state and B state. Okay. And the final state actually no difference. They just take D. So that's your final DFA that you can use to implement your Lexer would be like this, okay? So now we got the DFA and we are going to design the Lexer. So to design the Lexer, we actually have the scanner design, okay? So we can implement a scanner that implicitly capture the circle and the arrow structure of the DFA in two main different ways, okay? One way is we use the control flow of the case switch statement. Okay, that's actually EHAC implementation. And EHAC implementation, actually, we already introduced it. Second one is using table-driven and driver. Okay, so implementation 1 is EHAC implementation. Implementation 2 is automated tool generation. Okay, so writing a pure DFA set of the nested case statement is surprising useful technique. You can use a Perl, awk, and SID in Unix to do it, okay? And table-driven DFA is what Next and ScanGen can do, and the automatic generation. So the second part, we will cover it in the next lecture. So nested switch case, you actually started from initial state 1 and we in current character, and based on your current character and the input data, you determine what state you should transfer. So that actually is the EHAC translator, EHAC lexical analyzer. We already covered it. Okay. So the more important part is how you define your final state machine in a proper way. That actually is more important. Okay, that portion is more important. Other than that, actually, it's not that difficult. Okay, so that's the EHAC generator. And then you might need to have a look ahead. Okay, we actually implement that. So scanning in measure case, you may not be able to get by with any fixed amount of look ahead. Sometimes the look ahead may be more, okay. Sometimes may need assistance from parser. So that portion would be more difficult, okay. And note that the rule about longest possible token means that you return only when the next character cannot be used to continue the current token, okay. So you will terminate the token. So we have the token as a buffer. We continue to collect the token size. Say you may have a token starting with 3, then 5, then 0.2414, and then space. When you finish, it actually is a real number. Okay, so that you need to accumulate your token until it's the longer possible tokens. Okay. Okay, so that's actually a hard way, and you can also use the table-driven scanning, and you can build a two-dimensional transition table. Two-dimensional. So here, table-driven scanner is that you have a DFA that is okay, and basically you have state and input. So here, the table already here, your state and your input determine the next state. Okay. So that's called table-driven way. It's actually very apparent. Okay, the C language algorithms over here. Okay, and that here we have a pseudocode in the textbook. Okay, this one is in the programming language pragmatic chapter 2.11 figure. Okay, you will be able to see this the so-called pseudocode for it. And this calculator language that we actually study come with the table like this. Okay, come with a table like this. This state transition table, again, they are based on the result of your final state machine. Okay, and you can use a driver like this to drive it. Very, very straightforward. Okay, very, very straightforward. Okay, the rest of the chapter, we are going to cover the so-called extended Baker's norm form, okay, and also the regular expression. Section 11, EBNF, extended Baker's norm form. So EBNF format in this course, there are a few different typographic convention used in EBNF lecture. So right here, we use the Python documentation, okay, the format. So some of the symbol actually you do not try to insist on it. Okay, sometimes it actually a production rule can be used in this one, can be used in this one, can be used in assignment or even single assignment. That's okay. Based on the documentation tool, you actually should adapt different systems. So production rule can be defined as this, okay? And italic name is written as names, and you have quotes, okay, box characters, or string, okay, or string, you actually use quote. And parenthesis is grouping, okay, parenthesis grouping. And curly brace is actually used for the clean, okay, clean star, okay, plus for concatenation, or one or more time. I'm sorry, actually plus is one or more time. So star for clean star, that means that this one repeat 0 or more time. And then you have plus actually means the 1 or more time. Okay. Okay, let's actually look at this EBNF format. So basically, you have the derivation or production rule. Okay, bar is option, parenthesis is a grouping, and sometimes you have the two options in the optional set. Star is the repetition, go clean star 0 or more time. Plus means 1 or more time. It's equivalent to 1 time and then 0 or more time. So A plus equivalent to A star. Okay, 1 or more time. So because A star is always there, well, A plus become a new notation you can use. That's extended format. Okay, and quote 51 that actually is a literal. It's actually a combination of letters. So your digit is defined as this. Okay, integer defined as plus or minus digit with digit star, okay? And integer can be defined like this, okay? And integer can be defined like this, okay? This one or more times. So these are the digit rule, okay? These are the digit rules and written in the EBNF format, okay? And this EBNF format is using format specification mini language of Python library, okay? So right here, replacement field is like this, okay? Field, okay? These are a grammar for replacement field, okay? Whatever. Okay, grammar for replacement field. We'll continue with this. So these are just set up the different production rule for the in the EBNF format. Okay. Now next one, state diagram. State diagram is alternative to represent your EBNF. Okay. So EBNF usually is text format. So used for what? Used for the computer rule generator, okay? And syntax diagram you usually use for documentation and design, okay, and design use. So you have A or B followed by C, okay? So B followed by C actually is one concatenation, and A or B or B concatenated with C. This one is A or B and then concatenated with C, is like this, okay? This one's A and then B 0 or 1 time, okay, is like this, okay, optional B. And then this one is A, okay, this one actually is what? B bracket means B star, okay, B bracket means B star. This B bracket, okay, I'm sorry, this is B braces, curly braces, B star. This B with bracket actually means that B or empty string, okay, B or empty string, 1 or 0 time. 1 or 0 time, you will bypass, okay, or actually with B. So these are syntax diagrams. So syntax diagrams are not very typical. You have the optional rule, okay, and optional set, okay, 0 or 1 time. And you have possible repetition, clean start, okay, and 1 or more times repetition, and also grouping, okay. These are different rules for the syntax diagram. So here we do have the definition for digit, integer, real, and the operator term and expression like this, okay. So next one, we go into the regular expression. So EBNF can be used to generate the so-called table, okay? And regular expression can be used to generate the EBNF or can be used to generate the finite state machine as well, okay? And before we have the regular expression, we might design our rules in the syntax diagram. So syntax diagram is for design use. And then we can use that syntax diagram to design and then generate a regular expression. So right here, we have this one, very complicated. And this actually really means what? This really means your email address, okay? Your email address is written in this way. We will explain it later, but this one is email address, okay? And regular expression or regis describe a pattern of text that can test whether a string match regular expressions pattern or not, okay? So regular expression can occur in many places, text editor for search or replace, or you can use the JavaScript, okay, to do scanner or split or replace sometime, okay? And it can be used in the Unix, Linux shell grep or seed or file, okay? So this can be used in many places for using regular expression. So the one we talk about is an email address. That's user at the domain.qualifier. Okay, that's email address. And detailed rule we'll discuss it now. So here we have a cheat sheet for regular expression. Okay, so let's look at this cheat sheet right now. A cap sign means the start of a line. Okay, it actually is coupled with a dollar sign, that's the end of the line. So actually starting of the line and ending of the line, these two, okay? And you have backslash A means that it actually is what? Starting of a string, okay? Backslash G actually is ending of the string, okay? And backslash B is boundary, word boundary. Okay, so this one some rule for anchors. Okay, anchor means that where should you consider the pattern and where should you finish the pattern. Okay, character set, you have the D means digit, capital D means non-digit. Okay, W means word, capital W means non-words. Okay, backslash slash S means the space later, backslash capital S means non-space later. These are the important rules. Backslash means a single backslash. Okay, backslash quote means a single quote mark. Okay, so these are something we have. Okay, and you can also have the qualifier. Qualifier means that star means 0 or more time. Question mark means 1 or 0 time. Plus means 1 or more time. Okay, these are the quantity. And you can also specify 3 times. It's actually curly brace 3. Okay, 3 comma means that 3 plus time. 3 and 5 means 3 to 5 times. Okay, this one quantifiers. Okay, and you can also use the range specifier such as A to G. So A to G actually is the same as your single letters. So it's actually equivalent to /W. And if you have 0 to 9, like equivalent to your digit, okay, /D. So this one is a set, okay? You can also consider the bracket. Inside the bracket is actually a set of letters, okay? And you can have set A, E, I, O, U for vowel sounds, okay? That's a set. And if you have the cap, means that no A, no G, okay? This one is inclusive rule, okay? That's actually the inverse of that. Any letter, any symbol, but not A and G, okay? So this is a quick cheat sheet for it, okay? Let's look at the syntax of a regular expression. So it is used in JavaScript, Perl, and Python, and different language. Some of the implementation may be different. Okay, some of the implementation may be different. And the one we are talking about right here will be using JavaScript, okay? Because JavaScript is used for website design a lot. So let's look at the JavaScript format. JavaScript, you have the matching method, so you can use match. So some string matching with the regular expression, it will give you true or false, okay? And you can have a string replaced with some regular expression. For any string that matching the regular expression will replace with some text, okay? You can use to search for pattern and return the index of that first occurrence. So this one is equivalent to find or index of, okay? And you can split with some delimiter, and delimiter may be in the so-called regular expression format, okay? So these are the methods that you use usually in JavaScript. Okay, so basically there's a pattern. You start with slash, finish it with slash, okay? Some will not use it, but JavaScript will use it. So different language, some language, the pattern just use double quote, and put your pattern inside. Some would be using this in JavaScript, okay? Or even this in JavaScript language, okay? So that actually is the pattern. So above pattern and including ABC. So these are actually including ABC, okay? And these are not, okay? These are not. Okay, so wildcard. So if you have a single dot, means that every character except the changing line mark or backslash F, okay, some special letters. Okay, so here, any letter, it actually is any letter and the OO, any letter Y. So OOY, 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 this actually is a wildcard and anchor, okay? Okay, so dot is any letter, backslash dot, okay, it actually is matching for a dot. Okay, backslash dot is matching for a dot. Dot is any letter. Okay, so here, okay, and the cap is the starting of the line, a dollar sign is the ending of the line. So we want to use this one only to find the entire line consists only if. Okay, so this one is that the whole line only has if. Only this one will match. So if you have a line that is actually if A greater than B, no, that actually doesn't match it. Okay, doesn't match it. This one means that a string, a whole line start with if, start with I, ending with if, and only IF in there. And backslash less than, that is the beginning of the word. Backslash greater than, that's the actually ending of the word. And we can also have the so-called beginning of a string and ending of a string, beginning of the word and ending of the word. Okay, so this one is some technique you can search for the pattern. So those different anchor means that where you start to search your pattern and where you end the search pattern. Okay. Okay, so now we have a match. So match actually will match the pattern. So Obama match that A, okay, globally. Globally means that if there is any global, so BA and MA will be returned. Okay, these two patterns will have a match pattern will be returned. Okay, so that's globally. And then I actually case insensitive. So Marty or Marty this way, they all match. Okay, G outside the pattern. Okay, G outside the pattern means globally. Okay, matching everywhere. Okay, matching every globally. I means the case insensitive. And if you have the so-called replace first occurrence of it, okay, so you replace the S with X, so you actually first occurrence. Okay, if you have the S and globally means every S will be replaced. Okay, and then you have this one return, so replace S globally with this. Okay, now return the value. Okay, that must be stored. It must be stored. Okay, it must be stored back to it. Otherwise, it will return this, but you may not have a receiver. Okay. Okay, next one, special character. So you have A, B, C, or D, E, F, or G. Okay. So this one actually, A, B, C is one string, D, E, F is a string, this is this. Okay, so actually this. So here we have cat, okay, a subject or date, okay, versus this. Actually, there's no end sign. Okay. So this one, a bar means or. Okay, bar means or. Okay, end sign. There's no such thing as end sign. Or means optional, right? And you have concatenation. Okay, parenthesis means grouping. So you have a slash Homer or Marge. So Homer or Marge Simpson means Homer Simpson or Marge Simpson. Okay, this grouping. Okay. Backslash star with escape sequence. So here, backslash star means a single dollar sign. Okay. Backslash dot, that's a dot. And backslash is a dot splash n. Okay, that's the escape sequence. So here, quantifier star means 0 or more. So A, B, and then C 0 or more time. It's A, B, C, A, B, C, C, A, B, C, C, C. Okay. This one, A, B, C 0 or more time means A, B, C, A, B, C, B, C. Okay, A, B, C, B, C, B, C. A star, A dot star. Dot star means that any word, wildcard word, and 0 or more time. So it would be AA or ABA, AQA. Okay, something like that. Plus means one or more occurrence. Okay, and question mark means a 0 or 1 occurrence. Okay, so here Martina, A, okay, Martina or Martina, Martin or Martina, okay, you can use this, okay. And this question mark only affect the A, okay. If you want to have a whole Martina, you actually have to use a parenthesis, okay. So Daniel or Dan, this one actually is Daniel or Dan. Okay, quantifier, you can use a minimum, maximum, or a single number for the number of times. So only have a 3 is generally 3 times. 2 comma means 2 or more times. And comma 6 means up to 6 times. Okay. So that's a more quantifier. Okay, character set means that the whole thing in there. So BCD means that BART, CART, or DART, one of these. Okay. So it really is this one BCD is actually equivalent to B/C/D. Okay, it's actually equivalent, but shorter. Okay, and you have the bracket means that this whole thing, one of them and star. Okay, so one of them and star. So can be period, can be exclamation mark, can be star, or can be question mark. Okay, so it actually means this, or this. And because it's dot, okay, so it actually here really mean the dot. Okay, it really mean the dot. Okay, it doesn't mean the wildcard later. Okay, so A to G or A to G, A to D 0 to 9. So this is a single letter lowercase A to G. This one is lower or uppercase or digit. Okay, so kept ABC means that anything but not ABC. Okay, anything character but not ABC. And inside character set, so here you have backslash minus plus. Okay, so it's minus or plus 0 or more times. So can have the plus, can have minus or nothing. And then followed by 0 to 9, a digit, and 1 or more times. So this one is the what? This one, if you write into the syntax diagram, it should be a plus sign or nothing or minus sign followed by a digit or more time, which is something like this. Okay. This one is the so-called digit. Okay. Okay, so here we have BO in character range. B for boundary, okay, or boundary. D for any digit, and capital D non-digit is equivalent to this. Okay, backslash S means these white letters, white space letters, and backslash S is non-white space letters, and backslash W is this any letter digit or underline. So this one W means that ID words. Okay, ID words, and backslash W means capital W means non-ID words. Okay, so it can be punctuation mark or any symbol. And you can also use the backslash U for Unicode for other language. Okay, for the use of other language. Okay, red flags. Okay, you have pattern G for global matching. Okay, we all replace all. Okay, and you have the case insensitive with I. Okay, with I, and then M for multi-mode, non-multi-line mode. It will actually continue for many crossing the line boundary. Okay, Y for sticky. Okay, start with a given index. So you can have ABC global and I for case insensitive, okay, and matching any occurrence. Okay, back reference. Back reference is that you can capture, okay, capture. So this one is used to grouping and capture, okay, so capture. So you actually can have backslash number to refer to number, okay. So here you can have a question mark, these matching text, but do not capture, okay? And you have A question mark equal B, okay? A question mark equal exclamation B. So here, let's see, you have /1 for the first capture, /2 for second capture, okay? So here, surrounding by same character. So here, the first capture, okay, A, okay, surrounding A, okay, A surrounded by same character. So it actually first occurs or some later, capture later, okay. So here we can refer to capture on numbers. So right here we are our name, okay, our name replace the capture of the one or more word, comma with one or more space, and then this. So here you actually what? This is the first capture, you put it here. A second capture of the word, we put it over here for the grouping, okay, for the grouping. So grouping can be replaced in later with the number to replace it. This one is called capture, okay. So that's what we say as capture. You can use this one to really do a swapping of the first name and last name, okay. So that's the so-called capturing number we talk about, okay? Okay, so here we have a rigid object, okay? You have the R equals AB plus C global, okay? So this one AB plus C is any AB and case insensitive and globally matching it, okay? So that is a regular expression, okay? This one is regular expression. And this regular expression can be created and put into different match, replace, or different location to be used, okay? So here we have this one backslash slash slash. So this one is a slash slash and then one or more word.com, okay? So here is HTTP with or without S, okay? 0 or 1 time, okay? With S or no. And then backslash, here you have comma, okay? Comma and then backslash, backslash. I'm sorry, slash, slash. And then you have the one or more words, okay? One or more word. And then you have a dot. This one is dot, okay? So this one is a regular expression for HTTP with domain name, okay? So this one can happen on regular expression on the text editor, or it can happen on many locations. So we actually finished this chapter summary. Is design scanner need to start with the lexical analyzer, okay? In this section, we study to convert from the grammar rule to NDFA to DFA, and then use DFA to design ad hoc scanner or table-driven scanner, okay? And we have an example for ad hoc scanner and table-driven scanner. We will, in the next lecture, using the next tool to explain it, okay? And more detail for the regular expressions, okay? And before we end this lecture, let's actually look at some example. First one, we can go to a website for regular expression tester, okay? So right here, you can try out every single regular expression tester. So here, let's try the one we just see. You have HTTP, okay? And you may have S or no S, but you have question mark as 1 or 0 or 1 time. And apply, you have backslash, backslash, right? That actually is, you should have a colon before it, okay? And then after that, you have backslash, okay? You would have a W, so a word, okay? A word, so you should have the backslash W plus sign. I'm sorry, W plus sign, okay? That actually is a single or more letter, and then a dot, and then comma, okay? Something like this. Okay, let's see. Here we actually, we don't test this one. Okay, so let's do HTTP, okay? www.eco24.com. Okay, I'm sorry. Let's try this, okay? So this one, we have this one here, okay? And let's actually do, there's a one match, okay? There's one match. So let's try one more. HTTP of the google.com. Okay, there's a second match. Okay, there's a second match. So here you say two match. Okay, two match. Okay, and here we may have HTTP, okay, S, okay, and then we have the so-called request.com. Okay, so this we have three match. We all show you the matching part. Okay, let's try different thing. Okay, let's try different thing. So let's try to have some text. Okay, so declaration of independence text. So let's actually get this one. Okay, we actually get the whole thing here. Okay. Okay, so this actually is right here. Okay, we put the declaration of the whole thing. So let's assume that we are trying to find out the pattern that actually is with the leading capital case. So we have say we want to see the declaration. Okay, so that one we would like to find out some actually have, and we want it to be what? We want it to be a word, beginner word. So let's try this one. Actually, let's try this one. Okay, beginner of word, ending of the word. Okay, in between, we actually try to use a capital letter. Capital letter is capital A to G. Okay, this one actually need to occur at least once, right? At least once, and then we would have something only lowercase, so A to G. Okay, this one can happen one or more times. So let's see. Let's actually take out the so-called word boundary. Okay, let's take out the word boundary. Let's say take out. Okay. So right here, as you can see, it highlight the whole word that actually has a capital letter at the beginning. Okay. So this actually is the word that we can try to find out all of the word. Usually these are the pronouns. Okay, pronouns or the beginning of the sentence. Okay, pronouns or beginning of the sentence. So this is a way we can use it to generate. So we can try out the pattern, regular expression pattern using this tool. Okay, using this tool. And let's actually try a different way. So let's assume that we are using this one, okay, in demo 10, that's actually using the so-called declare text, okay. So let's actually create this declaration text, and we actually pass the whole declaration of independence over here, okay. But so let's assume that we actually have the whole thing here, and let's actually do edit. Okay, let's actually save all, okay, save all, and let's edit and do find, okay, do find. Okay, let's see. To find. So here we have the find pattern. So find pattern with this regular expression pattern. So we do have the capital A to G followed by A to G, lowercase a to G. Okay. And then this one is 0 or more time. And let's try it, okay. So no result. Let me take out this slash, okay. Let me take out this slash. So as you can see, the slash or non-slash. Okay, I'm sorry. Let me try one more time, okay. So here, let me try out find, okay. So we have a find box, okay. Here, let's do A to G and also A to G 0 or more time. And let's try regular expression. And here, let's do globally in case ignored. And let's see here, this one, let me see. This editor, let me see. Okay, let's actually do find in file, okay. Let's copy this pattern. Okay, it actually can search for the files. This one actually do not have it. Okay, let's try a different way, okay. Let's try a different way. So this one, this editor, Visual Studio Code, I'm not sure whether you can generate the right result. Now let me try a different one. Let's actually get to the same file, okay, get to the same file. Let me open it with Notepad++. So here, demo 10, we actually have this declaration of independence. Okay, and that actually do search. Okay, search that actually find. Okay, let's do find. Okay, let's do find. So find here, let me actually here let's actually pass it. Okay, so let's take out this thing. Okay, take out this thing. Take out a slash, and let's do regular expression. Okay. Let's see, A to Z, A to Z. Okay, let's see, rebel wrong. Okay. Here we have an in. Okay, so A to Z, A to Z one more time. Let's actually look at the pattern. Okay, let me use the slash. So here, let's see, rebel wrong. Okay, match case. We don't want to match case. Okay, so here, let's see. We search. Cannot find the pattern A to Z, A to Z. Let me try different way. Okay, let me try using backslash W, lowercase w, and also backslash over lowercase w. Okay, fine. No, it should not. Okay. I'm sorry. Here, actually, you can use for regular expression. So let me try this way. Let me try capital A to Z. Okay. Capital A to Z is searchable every single letter actually. Okay, it's searchable every single letter actually. So that's actually refine it. Okay, refine the pattern. So actually, we need to match case. Okay, we should need to match case. So right here, not in. Okay, that actually do A to Z. Okay, we need to match case, and then lowercase A to Z, and then star. So that's why all in current document. Okay, so here, as you can see, it will go through it. Okay, so here you have in Congress, July, the Declaration states American. So these are capital words. Okay, and as you can see, it's not as convenient as what we use in the website. Okay, but at least you can find each single one where they are. Okay, where they are. And Visual Studio Code, I believe, should have a similar option. So let's see, actually look at the file one more time. Okay, so let me don't try to use this JavaScript slash pattern. Okay, so let's do this one. Match whole word. Here actually match case. So we don't want to match case. We want to match case and match whole word. Okay, and there's no result. Okay, I'll look into here. So here, using regular expression. Okay, sorry. So here you need to touch this one for matching regular expression. So you will highlight all of the so-called words, okay, with this. So play around this, okay. Some editor do need to turn on some flag in order to make it work, okay. And this actually conclude our chapter 8A, okay. Chapter 8 is part 1, okay. And this one is, basically we talk about the design of the lexical analyzer. So we come from the grammar, okay, and we design a ad hoc scanner for it, and we convert the grammar into non-deterministic finite automata, then convert it to deterministic finite automata, and then we can use it to design the ad hoc scanner, also table-driven scanner. And at the end, we talk about the regular expression and how to use them okay, and also syntax diagram. But in the next lecture, we will be focused on using the regular expression, how to design regular expression, and also applying it into the automatic generation of the tokenizer. Okay, thank you. Bye now.